All right. So let's get started on 6.2. We're going to be talking about trig equations. Now that we know about inverse functions really well, we can talk about solving trig equations. I take a little bit of different approach to this than I think most people. And I take a different approach than your book does, that's for sure. So the examples that I work out, I usually try to pick different examples than the examples given in the book so that you have multiple examples you can look back on in case you didn't understand from class or whatever. But in this section, I'm going to use the exact same examples that the book uses so that if you don't like the way that I do it, you can try to read through the book and use their approach. But here's how I like to solve trig equations, okay? So looking at the sine function, if sine x equals k, then in order to solve that, you can take the inverse of both sides and get x equals sine inverse of k. And then plus 2n pi, where n is an integer, because, if this is a solution, you're going to have a solution every 2 pi units after that, or every 2 pi units before that, right? Because sine is periodic with period 2 pi. That's one set of solutions, right? The other set of solutions is going to be pi minus sine inverse of k. And then again, every 2 pi units after that and every 2 pi units before that, right? But the main idea is, you're going to have a solution here at sine inverse of k, and you're going to have another solution here at pi minus sine inverse of k. So I'm not going to give a detailed proof of this fact, but I'll give you a little sketch, okay? So notice that, so if k is positive, so if k is a positive number and sine x equals k, then that must mean that sine is in quadrant 1 or quadrant 2, right? Because that's where sine is positive. So, and if you're looking at x equals sine inverse of k, that would put you in quadrant 1, right? So x would be that angle right there, and in this case, x would be sine inverse of k. But notice that there should be another solution, okay? There should be another solution here in quadrant 2 because because sine is also positive here in quadrant 2. This solution should be pi minus sine inverse k. Okay, so let me draw out another version of these, right? So here's the other possibility. Okay, so the other possibility is that we're describing this angle right here, in which case its reference angle is still going to be sine inverse of k, right? So the reference angle is still sine inverse of k, but the angle itself is going to be pi, right? Pi minus sine inverse of k. So, and maybe if you already like this, I'll say x equals sine inverse of k, or x equals pi minus sine inverse of k. Right? So that's what happens when k is positive. I'm going to erase this and look at the case when k is negative. Okay, if k is negative and sine x equals k, then that must mean sine x is either that must mean that x is either in quadrant 3 or quadrant 4, since that's where sine is negative, right? So x must be in quadrant 3 or quadrant 4. Well, if we're calling x sine inverse of k, then that must mean it's here in quadrant 4. And in fact, sine inverse would mean that we're looking at the negative angle. So we're not talking about this angle, okay? We're not talking about that angle. We're talking about this angle, okay? So that is one solution, right? X here would be sine inverse of k, right? So that's one solution. But again, you could have another solution here in quadrant 3. So we want to describe, well, what's this angle? And this angle is also pi minus, so the reference angle here is still sine inverse k. Only it's going in the negative direction, right? So the reference angle going in the negative direction would be sine inverse of k. And that means this angle, I guess I should draw a new picture. So let me just draw a new picture actually. Okay, so here's one of the possibilities. The other possibility, right, is that x is here in quadrant 3. The reference angle would still be sine inverse of k. And so x would be pi minus sine inverse of k. Right? And you might be thinking, well, why isn't it pi plus sine inverse of k? Well, that's because, again, this is a negative angle. Notice the orientation, right? It's different, right? So you say pi minus sine inverse of k. For example, let's say that sine inverse of k is something like negative 45 degrees, all right? So then to end up here in quadrant 3, you wouldn't say 180 degrees minus 45 degrees. That would put you at, what is that, 135, right? It would put you here in quadrant 2. You want to be down here in quadrant 3, so you've got to say 180 minus negative 45, right? So it's 180 minus sine inverse k, or pi minus sine inverse k. Okay, so whether k is positive or negative, if sine x equals k, then x is either sine inverse k or x is pi minus sine inverse of k, plus every 2n pi after that or before that, right, where n is an integer. Okay, so that's the idea behind that one. We have similar statements for cosine and tangent. They're not exactly the same, but they are similar. So I'm just going to write them all out in one place so that we can see them all and kind of compare and contrast them. I'm not going to prove the rest of them, but we have this one for sine, right? So if sine x equals k, then x equals sine inverse of k plus 2n pi, or x equals pi minus sine inverse k plus 2n pi. All right, that's for sine. If cosine x equals k, then x equals cosine inverse of k plus 2n pi, or x equals, now for cosine, it's not pi minus cosine inverse, it's 2 pi minus cosine inverse. Okay, 2 pi minus cosine inverse. Okay. So you might have to give that a little bit of thought, but basically it's because, like, if your solution is in quadrant 1, you can have another one in quadrant 4, right? So you've got to go all the way around the circle and then subtract off that cosine inverse, right? Same way, if your solution's in quadrant 2, then you're going to have another one in quadrant 3, right? So it's 2 pi minus cosine inverse. And then finally, for tangent's the easiest one. So if tangent x equals k, then x equals tangent inverse of k plus n pi, and that's it. There's only that one set of solutions for tangent. But notice that because the period of tangent is only pi instead of 2 pi, right? It's the solutions are tangent inverse of k plus n pi, not plus 2n pi. Okay. So that's it, right? Now you may be wondering, how does that help us solve trig equations? Well, the idea, the strategy for solving a trig equation, or at least the strategy I'm going to employ, is that regardless of what I'm given, I'm going to try to whittle it down so that it looks like this, or this. Okay? And then once I've done that, then I'll apply the appropriate rule. And that's how I'm going to solve trig equations. So, so that's it as far as introductions are concerned. Let's work out some examples.